There we go. Ooh, that's doing interesting things with the colours. Okay. Well, we'll have a little bit of desaturated colour, I guess, for today, but nothing in this talk relies on accurate colour information, thankfully, so we will be all right. Right, we are now 2 minutes past, so it's definitely fair for me to start. Hello, everyone. Thank you for coming to see me speak today. It's a talk slot that's packed with really great talks, so I'm very honoured that you've chosen to be at mine. My name is Eli, and I'm here to talk to you about how we store data. This is a bit about me. I'm a freelance developer advocate, which means I get to go and talk to developers, find out what kind of problems you're solving with cool, interesting technologies, try and make your life a little bit better, and I get to learn whatever I want, which is really, really cool. So the talk that I'm giving today about the history of data storage came out of when I used to work at a cloud company called Scaleway. It's a small European French cloud company. And obviously, as a cloud company, what you do is you deal with the sort of storage and retrieval of data. So I got interested in how we do that as a species, how we do that. What historical sort of reasoning has informed the way that we do these things today. And this talk is all of the things that I learned. Well, not all of the things I learned, because it could easily be a couple days worth of talking, but some of the most interesting things that I learned that I think are useful for us as developers to know about. So this talk is worth, before I get properly started, defining what I mean by data storage and why this is interesting. And one of my favourite ways of illustrating this is in the Sherlock Holmes. So I'm English, and obviously one of the great English cultural exports, aside from colonialism, is Sherlock Holmes. And in the Sherlock Holmes stories, the titular detective he has this analogy where he says he doesn't know that the Earth revolves around the sun. He sort of just doesn't. That's not a fact that he knows, and he justifies this by saying that the inside of his head is like an attic crowded with furniture, and the fact that the Earth revolves around the sun is not useful to him in his line of work as a consulting detective. So he would, in order to store that fact, he would have to chuck out something else from his attic, something else that was much more actually useful to him. And one of the reasons that we store data as human beings is because of that same sort of idea, that analogy that we need to know more things than we can fit in our heads at any one time. And therefore, we need to store the things we need to know. But in order to store something, you need to turn it into a physical object. And so what data storage is the process of doing that, taking information out of our heads and turning it into objects that we can put somewhere, then later come back and get that understanding back out of those objects. So that's what this talk is about today, how we do that, why we do it the way that we do. So a practical illustration of this. How many people in this room know 3 phone numbers off by heart? 4? 5? Okay, it's a good handful. I probably know about that much. So one of the things that I'm going to talk about today is an example of storing that would be the phone book, right? And you go and you read and you know the number, and then you can actually use the number. But obviously data storage gets a bit more complicated than that. And there are 2 kind of aspects to data storage that I'm going to talk about today. One of them is the physical durability of whatever object we turn our ideas into. So with the phone book, right? It can catch fire, it can get waterlogged, the paper can get ripped. But there's another aspect to this, which is the idea of the encodings of the data that we use, the method we use to translate information into an object, and our ability to get meaning out of that object in the future. So if it's written in a language that you don't understand, for example. And one good example of this going wrong is, without getting out your phones, can anybody tell me where this leads? Right? Yeah, well, not necessarily, right? Sorry, I'll try not to be too percussive to this mic. Right, but this is data, and it's very, the durability of this data is pretty good, because an image that can just be copied and replicated infinitely. But without specific technology to extract meaning from this image, it's useless. So that's the other half of what I'm going to be talking about today, is the 2 sides to data durability. Physically, how do we store these things? But also philosophically, how have we turned information into a physical object? And is that transformation durable? So the structure of this talk today is I'm going to talk about some old things, pre-electricity, pre-computing methods of storing data, and how they rank up on this sort of ideas of durability. Going to talk about some fun history and computing stuff that people in this room may already know, some fun facts in there, how that stuff has led to what we use today and informs our current constraints, things that affect us in our actual daily work as developers. And lastly, for a bit of fun, I am going to talk about some cool potential future stuff, things that we may use in the future. No guarantees. I am not, I'm not psychic. I don't know, but things that are fun to think about, experimental things that you can go away and read up on. So, with that in mind, let's go and look at some stuff that has stood the test of time. And when I say history, I mean the Bronze Age. This is a clay tablet. These were traditionally not fired in a kiln. They were just clay that was marked and left to dry. And as a result, we don't actually have a lot of these today. We don't have a lot of these extant objects because if you leave clay to just dry and you don't fire in a kiln, it's not very physically durable. Some of the ones we do have, like the one on this screen, is actually the result. It was accidentally fired because it was in a guy's house and his house burned down. So as a result, we actually know about the person that this clay tablet, the writing on this refers to. And it was a guy called Ea Nazir, and he sold copper, and he was bad at it. And we know this because his house caught fire. This poor guy, he was a copper merchant, very shady, had lots of customer complaints. This is the oldest known written complaint. And we only know about it because his house burned down. So the writing on this tablet is Akkadian cuneiform. And for a long time, we could not read this. The language and the writing system was lost. And linguists in the 18th and 19th century, actually, they looked at this and said, well, this is clearly writing, this is clearly language. Can we reverse engineer this? And they did, which is sort of a great triumph of theoretical linguistics, really fascinating stuff. But so we have this situation where the physical object is very durable, right? It survived. This is from 1750 BCE, so we're talking almost 4,000 years at this point. But the encoding on it was actually quite fragile. We were able to recover it, but they're equally likely that we would not have been able to, and the information on this would have been lost. On the other end of physical durability, we've got things like pen and paper, or ink on parchment, pigments on papyrus, and so on. Again, the encoding here is a written language, so being able to get information back out of these objects is dependent on us understanding that written language. This photo is of the first 2 pages of the Beowulf manuscript, another thing from my country of origin. And this was produced sometime between 975 and 1025 Common Era. So we don't know when the poem itself was originally written, and this is the only copy we have. If anyone studied the history of fantasy writing or Old English stuff, this is a foundational text. This is one of the things that Tolkien actually drew heavily upon and would have studied in order to write Lord of the Rings. So this has been an incredibly influential text in a lot of ways, and we've only got the one copy. This manuscript, for a while, formed part of a library called the Cotton Library, named after a guy called Cotton who had a fondness for old and weird things, much like I do. And this library was stored for a while in a place called Ashburnham House. Does anybody want to guess what happened to Ashburnham House? It caught fire. And unlike with clay tablets, fire is very bad for the physical durability of things written on paper. And a lot of the library was damaged as a result. Some texts were lost forever. The Beowulf manuscript did survive, but it was damaged in the fire and continues to accrue damage over time afterwards as a result. We've never lost the ability to read Old English, but the physical durability of this medium was really, really fragile, and we almost lost this incredible foundational text as a result of its physical durability being so fragile. Now, this is all very interesting, but this is a tech conference and I'm here to give a tech talk, so you may be thinking, what does this have to do with technology? And I now get to tell you one of my favorite facts. The English word technology comes from the same Proto-Indo-European root as the word for textiles. Historically, this makes a lot of sense because textiles, for a long time, were like the site of technological innovation. As humans, things we need to do are grow enough food to eat, find enough shelter so that we don't die of exposure, and make enough fabric to use for things like clothing and sails for ships. So for a long time, the primary pursuit of what people were doing was focused on one of these 3 things. In illuminated manuscripts and medieval art, you can often see women with drop spindles. This is a drop spindle. The small thing that she's holding on here is a drop spindle, and this is a distaff, and she is spinning fiber into thread. And you can see that her cat is bothering her, which if you have a cat, you know is absolutely true to life. And this is because if you were a woman in the 13th, 14th century and you had 5 spare minutes, no, you didn't. You were using that to spin fibre into thread for use in making fabric. This is where we get the English idiom to spin a yarn, meaning to tell a tale, because people would sit round doing this and tell each other stories to keep themselves occupied, which I think is really, really cool. Now, this was a very time-consuming and labour-intensive pursuit. And weaving thread, once you had it into cloth, was equally time-consuming and labour-intensive, until in the 2nd century in China, people invented the draw loom, which mechanizes this process, and it helped streamline the process of fabric manufacture, which is fantastic, right? And you can see this fabric has got some nice stripes on it, and it's very colourful and beautiful. People need fabric, but what we like is fancy fabrics. And it's possible to make fancy pattern fabrics using this kind of draw loom, but you come back to it being very labour-intensive, very fiddly. You have to select each thread. What happens is you've got these threads that run up and down, and these are called the warp threads, and you've got threads that run back and forth, and those are called the weft threads, and that's where we get the word weaving. And what you can do is, if you've got lots of differently coloured threads, when you separate the warp threads out to pass the weft through, if you choose them based on their colour and according to a pattern, you'll get fancy pattern fabric as a result, right? But this is very labour-intensive. It involved somebody, a draw boy, usually a child operating, like doing some part of the loom operation, to go and pick the threads out individually. Very error-prone, very labour-intensive, very expensive. But it's all according to pattern data, and it would be really, really cool if we could mechanise that aspect of it as well, which is exactly where we get punch cards. How these work is that each time you want to pick a thread out of those warp threads, a little hook comes down, and it's sort of a bit more complicated than I'm about to describe, but the basic idea is that if there's a hole in the punch card, the hook is able to make a connection, pick up the thread, separate it out from the rest of the threads, and if there's no hole in the punch card, the thread is left where it is. So for each weaving, for each time you want to separate those warp threads, you can actually encode that information into a punch card. The machine will be able to read that information and mechanically do the correct thing to produce fancy pattern fabric. Massively decreases the amount of labour time, massively decreases the error rate. This is incredible, and you can get fancy fabric with very little effort, comparatively. Here's some fabric woven with one of these punch card operated looms. The ideas behind this were developed by a few different French artisans and inventors in the 1700s, ending with a guy called Joseph-Marie Jacquard, and these are called jacquard looms or jacquard heads as a result. These patterns from punch cards from the 1700s can still be in use today. And while individual punch cards may not be that durable, although they often were made of like wood or ceramic, so actually they can be fairly physically durable, the ability to copy the information on them and have that information still be readable by modern machines means their encoding is actually pretty reliable. So the data durability from punch cards for use in looms is actually really good, which I think is really, really cool. So hold on to the idea of punch cards, because they will come back, as I'm sure many of you know. But this is one of the first examples we have of the data on a piece of in an object being for use and consumption by a machine and not a person. Skilled loom operators might be able to look at a card and recognize the pattern and maybe figure out from first principles what the resulting fabric will look like, but that's not their primary usage. Their primary usage is for a part of a broader machining context. And so this is there are different ideas as to what the first instance of that is in sort of human history, but this is a really well-documented example where actually the encoding is not meant for human consumption. And that's important because if you didn't have a machine to use that punch card, it's not useful, unlike being able to read a manuscript, for example. All right, punch cards, very, very cool. I love this part of history. We get it from fabrics, and now we've got computers, and it's really cool. So film photography is another method of data storage, and this is the earliest image derived from a photographic process. Whether or not you call it a photograph is up to you. The original photographic plate is here on the right, here on the left, and on the right is a colorized version of the resulting image. Is anybody here a film photography nerd? Knows anything about the history of film photography? A little bit. This is really famous in that field. It was originally created by a guy called Nicéphore Niepce in 1826. And he used a camera obscura to project light onto a plate coated with photographic substance. That substance would either harden or not harden in response to the presence of light. And you'd get a textured object as a result, which you can then turn into an image. This is really interesting as far as data storage goes, because the encoding itself depends on the photographic sort of material that you're using, but also it's a very direct response to the actual light information that's coming in. So it's in some ways a very faithful representation of the physical state of the thing that it's trying to record, in a way that, for example, writing something down isn't, where it's passed through the mind of a human in the way that the light captured by the photographic process hasn't. Obviously, what we choose to photograph and how we choose to frame things has a human element, and it is an art form, but the actual process of data capture is a lot more direct and faithful than a lot of others, which I think is really interesting. This is a daguerreotype. It's a sort of evolution of the photographic process from the late 1830s, taken by Daguerre himself, the person who gives these kind of photographs his name. It's very possibly the first candid photo ever. So in there, you can see a guy getting his shoes shined. And they were probably there for about 4 or 5 minutes, because that's how long exposures took with this kind of photography. And they're the only people who show up in the image, because they're the only people who would have been still, or relatively still, for that long. People were walking up and down this street at that time, but they weren't captured on the film because they didn't stay still long enough. These people did. And they probably never knew that they were the subjects of the first ever candid photo. It's just really, really cool. Obviously, film photography has continued to develop. Photographic processes have continued to improve. We have new materials, and it's still very much an active field today. Really, really interesting, given that none of you are film photography nerds and aren't going to sort of come up to me and tell me interesting facts afterwards, but it's really, really cool, really interesting to get into and read up on. So next thing, vinyl audio records, is the first example that we see in this talk of a paradigm that comes up over and again, which is you have a disc, and the disc spins, and you have a head that reads information off it that's written to the disc in a spiral. We see this again and again and again in data storage from this point onwards. Is anyone here a big vinyl nerd? Anyone collect vinyl records and use them? Oh, wow. Normally there's like a bunch of hands that go up for that point. So vinyl discs have a single spiral track that runs outward from the middle, and data is encoded on this by variations in the surface of the disc. So texture is the encoding. And the head is just a little needle that traces those dips and bumps and uses various mechanisms to turn those dips and bumps into sound. Modern ones use electricity to do so. Data here is encoded in texture, and the disc itself doesn't have a protective casing over it, which means that the physical durability of these things is really quite fragile. You have to be very careful when handling them. Fingerprints, grease from your fingerprints, scratches on the surface of the disc will all cause degradation in the data that's encoded within them. That's why we get the phrase, like a broken record, meaning repetitive. Because if there's a scratch on the surface of the disc, it can cause the head that reads from it to jump back a certain amount and then repeat the same bit of data over and over again. So physically, they're pretty fragile. And they're also dependent on specific technology in order to read the data back off them. You can collect vinyls, but if you don't have an actual record player, you won't be able to turn them back into music. However, you're able to get a very high level of definition, specificity in the data recording, which means that they are still beloved by audiophiles around the world. Right, that brings us on to some history of computing stuff. Now we are cooking with magnets, electricity, magnetism, computers. And we get punch cards coming back again, punch cards round 2. So a guy called Herman Hollerith developed punch card machines for tabulating census data in the US in the 1890 US Census. All that data was stored on punch cards. He later founded a company which got merged with a few other companies and became the institution we know and love today as IBM. The concept here is the same as with the looms. A hole in the card allows a connection to be made. And in this case, the connection was electrical. A spring dipped down into a pool of liquid mercury, which is obviously very safe and fun to be around. Computing has got a lot safer and a lot more health and safety friendly over the last 130 years. Something you might notice is that this punch card has 80 columns. And this is where we get today's widespread usage, although less so these days, but of 80 character lines. Because each line, so this represents one character vertically here, and you could encode 80 of them on a single punch card. That's where we get, old terminals that are like, no, you can only have 80 characters per line. So this sort of historical quirk of that's simply how big the punch cards were physically persists into the modern day in various aspects of our developer experience. Punch cards for data input and tabulation, where they were eventually succeeded by magnetic storage for most purposes. And that's what we're going to take a look at now. This is drum memory. This is more spinning things, or things that can spin and then heads that read off them. So magnetic storage is one of the primary things that we do for data storage today, and it works like this. You have a ferromagnetic material that coats, in this case, the surface of a drum. That's iron, cobalt, nickel, certain rare earth metals, and you arrange it in it's in a crystalline structure, which allows it to be magnetized one way or another, ones and zeros. And then you have a head that can read that polarity of the magnetism off it and retrieve the information that you've stored as magnetism in this surface material. So here, data is stored in tracks, which are sort of rings. If you imagine the drum like vertically, tracks that they're like donuts around the edge of this drum. And then you have heads that can read from the tracks. This is it's a Polish drum memory. It's called the ZAM41. And this has lots and lots of heads for reading and writing to the surface of the disk. The more heads you have, the shorter a distance any given head will have to travel physically to the point where data is stored to read that data off. That time is called seek time. And you want to minimize seek time for faster access to memory, especially if this is being used as the primary memory storage for your computer, which these were. However, more heads, more expensive, harder to maintain. So as with many, many things, there's trade-offs here between sort of speed and expense or cost of maintenance, essentially. And so with these, the physical durability of the medium, magnetism is pretty stable, especially when you're doing it in fairly comparatively large areas, which these were. So fairly large. We'll get on to magnetizing small areas later. But these were fairly stable in terms of the physical, like whether or not a bit of magnetic material was polarized one way or the other. That's pretty durable. And they're pretty hefty. It's not easy to damage them as easily as, for example, a vinyl record. However, your operating system, whatever's reading these ones and zeros, needs to know how to turn those ones and zeros back into something that's meaningful to a person. So the encoding is getting more and more abstract as we move into the world of computing. Right, and these were eventually superseded by various other kinds of memory for computing working memory, the most famous of which and the most long-standing of which is magnetic core memory. This is the dominant form of random access memory for a long time, so ubiquitous that it was just referred to as like core memory or just core. You've got all these rings of magnetic material, and they represent bits, and they have multiple wires running through them. And when you pass current through those wires, it will polarize those magnetic rings one way or another. Reading from a core also requires passing a current through, it will reset the core's state. So you have destructive reading. If you've got data stored in one of these cores and you want to know what it is, you're going to have to wipe it as well. And that's the first time, you don't read a book and the words disappear as you read them, right? But that's what's happening here because of the physical way that we've stored it. Again, magnetism is pretty stable, but if you don't know how to interpret the magnetism that you're getting out of these things, the data that's stored in them is not useful. One neat fact about this is that it was, like these days, in order to make your computer more efficient, we cool them down. With core memory, the constraint that makes them most efficient is consistency of temperature, not any given temperature. And it's a lot easier to heat things up than it is to cool them down. So these were heated to improve their efficiency. If you ever find that your PC is getting too hot, take advantage of it, install some magnetic core memory. Using smaller and smaller cores obviously increases the physical density of data that you can store in the same space. You can store a lot more data, which is a good thing in general, but it means it's much more expensive to manufacture. You would have sort of this threaded by hand, like getting these tiny, tiny cores with tiny, thin wires. And it was a very labor-intensive process to manufacture this core memory. It was eventually superseded by RAM for memory. One thing I forgot to mention earlier is I'm covering non-volatile memory during this talk. So I'm not going to talk about RAM because that loses its power. When it loses its power, it loses its state. I'm talking about objects that do not require power in order to encode data. And this, while it was the precursor to RAM, did not require power to retain its data because it's stored in magnetism. And that meant that if your computer crashed in the middle of doing something, its state at that time would be stored in this core memory. And that's where we get the phrase core dump from, because you could go and look at exactly what the state of your computer was at the time that it suffered some problem that caused it to crash. Right, more magnets, more wires. This is a piece of software. Core memory, core rope memory, was a form of read-only memory where writing to it is done during the manufacturing process. The order in which you thread wires through these rings actually encodes data. and it's a topological-based memory system, which is really, really cool. To update this software, you've got to do all sorts of threading and unthreading. And this type of memory got the name of little old lady memory, or LOL memory, because it looked so much, the process of manufacture looked so much like threadcraft. See, everything comes back around to the woman with the distaff and the cat chasing her thread, right? The most famous usage of this was in the Apollo missions. And it was perfect for that because physically, it's incredibly durable. You know, you don't get bits flipping because it's to do with the topology of wires threaded through rings. This is very, very resistant to any kind of corruption, right? And that's exactly what you want when you're writing software that you want to be absolutely certain is going to be exactly the same when you get to the moon versus when you sent it off. And I just think that's really, really cool. That's a piece of software in hardware. I just think that's incredible. Right, and now we get to something that I feel very old, putting it in the history of computing section, and that is floppy disks. Seen here in 8-inch, 5.25 inch, 5.25 inch, and 3.5 inch sizes. These were the latest and greatest in removable media storage from about mid-1970s to the early 2000s. And they're called, has anyone taken apart a floppy disk ever? Yeah, right? That's why they're called floppy disks. They're floppy disks because you take the case off, and inside is a floppy disk of magnetic recording material, again, ferromagnetic recording as the medium. And like drum memory and vinyl records, they are spinning disks where you have a head that reads off data as the disk spins. Here you can see a naked floppy disk. You know, if you pick this up and shake it, it goes boop, 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 boop. And closer up, it looks like this. This is a picture that was taken with a magnetic field camera, and what that's doing is it's actually taking photographs of the magnetism of the surface of the disk at each point. And so the bright and light parts represent, you know, ones and zeros. And you can see it's very slightly curved, like it's sort of the center of the floppy disk is somewhere over here. So you can actually see that spiral structure. And because the magnetic medium is what you are using to store data, they're very fragile when it comes to being near magnets. This is not true of hard drives, which we'll get onto, because they have a lot of more protective casing around them, and for other reasons that I'll talk about a little bit more. Floppy disks, not so. This is where, you know, I grew up using floppy disks, and I was always like, oh my gosh, can't let a magnet get near them. Because if you put a magnet near a floppy disk, it will wipe all of that data, right? I really, really hope this is a joke. This is, you know, one of many such images you can find online. And when it comes to spinning disks, and storing data on spinning disks, there's an idea that's common to all of those things, or a fact that's common to all of these things. So when you store data, and you store it like for a given chunk, for a given slice of your disk, right? This is called a sector of your disk, and memory is commonly addressed by sector. When you spin a disk at a constant speed, a constant angular speed, and you've got data that's stored in this sort of in concentric rings or a spiral, you can store the same amount of data on here as you can on here. And when we think about what that looks like physically, it looks like this. You've got 3 blobs of data, and they're stored quite close together. And out here, they're much further apart. Now, you know that you could be storing it more densely because you're doing it here, and it's the same kind of material as out here. But because of the constant angular velocity of the disk, you can't store it as densely. This is inefficient. Ideally, we'd be able to store data as densely out here as we do in here. But if we did that, we would have to vary the rate at which the disk spins depending on where in the disk we are reading from. People have experimented with this. Apple experimented with doing this in early Macintosh computers. They had a system where the disk spun more slowly as you read from the outer edge, allowing you to store data much more densely on the magnetic medium. This required unique drivers and unique floppy disks, and disks written with this system could not be read by disk drives that did not know about this system. The encoding was incredibly fragile. Even though the same stream of ones and zeros might be interpreted the same way by the different computers, the physical medium of encoding those ones and zeros was implementation dependent on these specific drivers and disks. So actually, the data durability of it was very bad because it was dependent on an incredibly specific hardware implementation, not just floppy disk drives in general, but specific ones made by these specific people at the specific time. It was incredibly expensive, it never caught on, and those disk drives went out of manufacture. So if you have a floppy disk written in that way today, I'm not sure you can get the information back off, even though the magnetism may still be good. Before computing environments were regularly networked, floppy disks were the go-to method for storing and sharing information between different computers. Of course, this legacy lives on, with the floppy disks having become the symbol for the save icon, right? When I was writing this talk, the number of people who came up to me and said, "Oh, you're doing a talk about the save icon," as a little joke. 50-year-old software engineers who absolutely knew that they were being obnoxious, which are just delightful. I think I'm up to about 17 people having made me that joke before. But obviously, we don't use these much anymore. Eventually, other data storage formats have become more competitive in terms of speed, cost of manufacture, density of storage. In 2003, Dell announced that it was no longer going to ship floppy disks as part of its flagship home PC. By 2007, only 2% of home computers had built-in drives. Floppy disks are coming to an end. Wikipedia calls them obsolescent, which I think is an incredible word. However, they are still around. This article is from 2019. So as David said in the keynote, technology, it takes a while to cycle out. If you love floppy disks, you can probably still find uses for them. Don't worry about needing to reskill in AI and WASM and whatever. Floppy disks have only recently stopped being used in the US, is it the Navy? Nuclear weapons, which might be the Navy, I don't know. Floppy is only mostly dead. You can still buy external floppy disk drives to connect. I think only 3.5-inch ones. I haven't seen any available on Amazon for larger floppy disk sizes. I couldn't find one with a USB connector. They were all USB-A. So maybe as we move away from USB-A, floppy disks, maybe that's the thing that will finally kill floppy disks. But if I wanted to read a floppy disk from, that I had from when I was, 10 years old and writing homework to take in school on one of them, I probably could. I could buy a floppy disk drive off Amazon and read it, as long as it wasn't one that was written with the Apple Macintosh variable disk velocity, angular velocity drive system. Yeah, obsolescent, just what an incredible world. Right, that brings us on to the modern day and things that we use in our everyday life. This is stuff we're familiar with. And first up in this section, we have more spinning disks, if you can believe it. Hands up anyone who has a desktop PC with an optical drive in it. More than I thought. Hands up who has a games console with an optical disk drive in it. Yeah, more, right? I sort of went, oh yeah, these are old, we don't use these anymore, but we absolutely still do, mostly in gaming. Is you ask a crowd of 20-year-olds that question, and it's a lot more of a stark comparison. So here under this category, I'm going to group together a lot of things that are all sort of very similar. So optical disks includes Laserdisc, CD-ROMs, writable CDs, DVDs, Blu-ray. They all function very similarly, and the things I'm going to talk about are common to all of them. And yeah, they're spinning disks. Data is arranged in a spiral track, and you spin the disk and read something off it. In this case, the way that it's encoded is, I'm really glad that the color for this photo or this image is not all booked, because this is probably the one time where you actually do want to look at the diagram in detail. So like with vinyl discs, it's texture it's used to encode the data. But instead of something physically reading that texture, like with the needle on a record player, here what happens is that the textured surface is covered in a reflective layer, which is often aluminium. And then over that, you have a protective layer of acrylic, and then you maybe optionally have, a label over the top of one side to protect it. And what happens is when you read a CD-ROM or any kind of optical media, this is the read-write head, and this is an Acer laptop optical disk drive, I think specifically a CD drive. And what it does is it points a laser diode at that surface, and judging by the reflectivity of the surface at that point, which will be affected by what the texture is, it can read the texture in that way. So you've got a laser diode that points at it, shines a laser, something that also then reads that laser back and can interpret the texture of the disk to get back the encoded information. CD-ROMs, ROM standing ROM for read-only memory, were developed by Sony in 1984. But it wasn't until 1997 that we got rewritable CDs. Read-only CDs are really cool because it's a texture that never changes, right? Because it's read-only. You can mass produce them by physically stamping out, by physically mass manufacturing discs with the correct texture on. So if you get my Mumford & Sons CD that I bought in 2010 or whatever, that was produced in that way, which makes them incredibly easy to manufacture on a mass scale. Rewritable ones, however, are a little bit different. This is a rewritable CD. What you might notice about this is that the reflective surface is a lot darker than the image we saw a couple of slides ago. And that's because it's not aluminium that's the reflective layer here. It's actually silver, indium, antimony, tellurium alloy. Try and say that 3 times fast after the party tomorrow night. What this does is it allows that laser diode in your optical disk drive to write to the CD. So instead of changing the texture of the sort of layer underneath, what it does is it melts this metal, turning it from a crystalline structure into a sort of solidified goop. And what that does is it changes the reflectivity, which is exactly the property that the laser diode is reading from to interpret data. So you're sort of faking texture by changing the reflectivity of the material directly. And this is really, really cool. In order to reverse that process, to turn your solidified goop back into a nice crystalline structure, you have to heat the CD up quite hot. And you have to do it all, you can't do that locally. You have to heat up the entire CD all at once. So if you want to wipe a rewritable disk, you have to wipe the whole thing at once. And reading data out of an optical disk requires its surface to be legible to the laser. So when we come to think about physical durability of the object, these don't have protective casing built into them. If you get, again, with like vinyl, if you get fingerprints on them, if you get scratches, it damages the availability of the data to the thing that is reading off them. You can also physically break them quite easily. This is a still from the Slow-Mo Guys video. So people who did sort of, 20 years ago or so were doing like slow-mo recordings of stuff before slow-mo cameras were widely available. And this is them spinning up a CD so fast that it just shatters. This is quite hard to do, but you can snap them. If you do that, it's game over for the data that's on it. As with all other computing sort of things in this section, the encoding of the data is also machine dependent. I can't pick up a CD and know what the ones and zeros are on it. I need a machine to do that, and I need a machine to interpret what that actually means in terms of meaningful information. Right. Magnetic tape storage. Here we have the first example, really, I think, of a data storage medium which is not random access. So with hard drives and floppy disks and flash memory, which I'll talk about next, you can access memory from anywhere on it in reasonably constant time. Like there's a fairly low upper bound on how long it takes for the head of a record for you to pick it up and move it to listen to a different bit on your record or whatever. With magnetic tapes, it's all stored serially. So if you were renting your VHS tapes from Blockbuster back in the day and you wanted to skip bits of the movie, depending on how much you wanted to skip, it would take you longer to get there. So tapes are made of ferromagnetic material, which we're all familiar with by now, magnetic material that is able to be polarized one way or another. The hardware that reads and writes to these tapes is known as a tape drive. Here are some old tape drives. These were used to record computer data in 1951 for the UNIVAC 1. IBM quickly followed suit and set the industry standards. Magnetic tapes have been in pretty constant use ever since then. And despite their drawback of having fairly long random access times, they're very useful for certain use cases, like cold data storage. Someone here use cold data storage as part of their work, like send records off to your cloud. Yeah, exactly. So cold data storage is what we call storage types of data storage which you don't need to access very regularly. It's okay if it takes 24 hours for your financial records from 6 years ago to become available because somebody needed to go to the data center, pick up a tape, put it in the machine. Like that's actually an acceptable drawback. And for that, what you get is very, very stable data in the sense that the magnetism is very, very physically stable. You can get a tape, write to it, put it in a drawer for 10 years, and then come back and be able to read the ones and zeros off of it. So physically, they're very, very stable. And they are used today in a lot of cloud companies' cold data storage. And one of the things that got me into writing this talk was learning that that's not actually how Scaleway does theirs. On the note of writing to a tape drive, writing to a tape, putting it in a cupboard for 10 years, one of the most famous examples of a very important, nearly completely losing some important data was the 1976 NASA Viking Mars lander. Seen here, a replica next to Carl Sagan. We didn't actually put Carl Sagan on Mars. And it recorded a bunch of data to magnetic tapes. NASA then got the tapes back when the lander came back to Earth, and they got these tapes and they got them out of the lander and then they put them in a cupboard for 10 years. I don't know why, but they did. And by the time they found these tapes and said, oh, we should probably read the data off of this that we spent millions and millions acquiring, all the people who'd worked on the original systems had either left NASA or died. So the magnetism was still good. The ones and zeros were all still there, but they'd completely lost the ability to decode it. And they got to put together a team who went to try and reverse engineer this encoding, much like those linguists from the 19th, 18th century for Akkadian cuneiform. They involved, the process of decoding this involved actually going to look at the physical lander to try and reverse engineer what it was doing when it was writing to those tapes. And they did manage to retrieve the data, but very nearly they didn't. And if the physical medium of storage had been more volatile than magnetic tapes, that data might have not been in a good state by the time they actually came to read it. So that's magnetic tapes. Hard drives. We all know and love these. Unless you're like an SSD-only person, you probably have one in the computer that you use all the time. You get them built into most personal computers these days. And you can get external ones that you fill with lots of pirated media. I checked the other day, and it looks like 20 terabytes is pretty available commercially. Wikipedia says 26 terabytes is available, but I couldn't find it on Amazon. These are spinning disks. Again, I wasn't kidding when they said there's lots of spinning disks. Things spin round, another thing nearby it reads data off of it. And the medium is, again, magnetic storage. So don't put your electromagnets too close to these, although they have a lot more protective casing built around them and various other things to prevent like magnets being near them from causing too many problems. Once again, it was IBM who pioneered these. These first came out in 1957, stored a whopping 3.75 of God's own megabytes per hard drive. Here are two of them. They had 52 disks each and one ARM that held two read-write heads. IBM kept iterating and improving on these. They also briefly flirted with a model that had one read-write head per track, like that Polish drum memory that I showed earlier, which meant it had a very low seek time. These turned out to be expensive and difficult to manufacture, and they didn't keep making them, something of a theme. And over the 1980s, these went from being very expensive as a sort of expensive add-on to your PC to being standard issue. Here we have another close-up photo, again, magnetic field camera, just like the one for the floppy disk. And one of the things that makes it less risky to put magnets to these is we have now got to the stage where the areas of the disk that we are magnetizing, in order to get better density of data, we're magnetizing really, really tiny areas. It's more than 50 nanometers. And for reference, like a piece of printer paper is somewhere between 70,000 under 180,000 nanometers thick. We're talking really tiny here. And when you start magnetizing areas that are that tiny, you become vulnerable to a quantum effect called superparamagnetism. And what that means is that heat, fluctuations in heat, can cause random polarity flips in magnetized materials. So just sort of random fluctuations in heat can mean that that one bit here flips from 1 to a 0. Depending on what bit that is, that could be really, really bad. And we made the magnets so small that the universe doesn't like it. Like, that's so cool. The way that we counter this today is each disk is actually two disks magnetized oppositely and next to each other, but separated by a 3-atom thick of ruthenium, which is not magnetic. And so those two magnetized disks stick to each other. They attract each other and they reinforce each other's magnetism. And we did this to counter the effect of we made the magnets too small. I think that's so cool. And one of the reasons I wrote this talk is because this is how my previous employer, Scaleway, does its cold data storage. This is a bunker that they have underneath Paris. I don't know how close it is to the catacombs. And these are like the only photos of it that are available. I couldn't get any better photos. The hard drives in this bunker store data differently than the ones in your PC at home. Right, so in your PC at home, the way that it stores data is there's a read and write head. And the area that is written to by the write head, you can imagine it's like a big wide ribbon going around the circle, going around the disk. But the read head only needs to read from a fairly narrow strip of that. So you're actually writing to a fairly large swathe of the disk, more wider than you need to. And this is inefficient, but for everyday use, this is pretty good because it means you can randomly write to anywhere in the disk, and you can be sure that you're only overwriting one track at a time. With these hard drives that Scaleway uses, what they do is a thing called, and the paradigm I just described is called parallel magnetic recording, because you can imagine that your write head and your read head are sort of in parallel with each other. The ones in this data bunker use something called shingled magnetic recording. And what this means is you start from the center and you're writing this fairly large, wide band. And then the next track out, you don't move one whole unit, all that width, you move slightly. So just enough that the read head has enough of the previous band to read from, but you're overwriting quite a lot of it. And then you write the next track out, and then so on and so on. And so you're sort of building up this sort of iterative, this magnetism, and you're overwriting stuff as you go. And what this means is that the data that you store is very, very dense. You're only leaving the band that's wide enough for the read head to read from it. But if you want to go and then you imagine you've got this very sort of like very narrow bands. If I wanted to go and write somewhere in the middle of that, I'd suddenly be overwriting many, many tracks at once, which means that you cannot do random write with this kind of magnetic recording. And that's fine for cold data storage. You usually want to write a lot of data all at once, and maybe you want to do random reads, but you rarely want to do random writes with this kind of storage. This would be so annoying for regular everyday computing, where you want to be saving files and you want to be doing, your sort of working secondary memory for your computer. But for cold storage, it's absolutely fine. And you can get a lot more density of data storing with this shingled magnetic recording, because it's like the shingled roof, sort of, than you can with parallel magnetic recording. And I learned about this and I thought it was really, really cool. I'd never known that you could do that with a hard drive. Again, if you take, like with the variable angular velocity floppy disks, you need to know which one you're working with if you want to get data back out of it. The way that we physically write the data to the medium has a huge impact on what you're going to get out if you try and read. Yeah, if you take one of these hard drives, shingled, and then you put it in and you try and write to it in a parallel mechanism, you're going to wipe out far more data than you intend. Right, last but not least in this section, flash memory. You have some of this in your phone, you have some of this in your pocket. It's in smartphones, tablets, if you've got a YubiKey, that's got flash in it too. And they work by using a circuit component called a floating gate MOSFET. And it's very complicated, but essentially what it does is it can store electrical charge. It has electrical charge, or it doesn't, ones and zeros. That's pretty much it. They have a few limitations or drawbacks. MOSFETs will wear over time. Every time you put charge into or out of them, they'll get a little bit, they'll wear out. So there are sort of lifetime limits on how much you can write to a given piece of memory within a flash drive, including SSDs. This lifetime limit is improving all the time. You're unlikely to actually hit it if you are doing sort of personal use SSDs. But to counter this, each flash drive will have something called a memory controller, and that sort of tries to even out the wear of reading and writing to memory across the entire drive, so that you don't get one bit failing way before the others and rendering your flash drive unusable. They should all sort of give at the same time, sort of equally, and they'll share the load, essentially. MOSFETs also leak charge over time. So a flash drive that I wrote to 10 years ago, put it in a drawer, I might not be able to get good data out of it at the end, unlike magnetic tapes in the Mars spiking lander. They're not physically durable over long time periods. And then when it comes to encoding, again, implementation specific to, like, we need computers. I can't look at this hard drive, this flash drive, and know what's on it. Need a computer. The computer needs to know how to interpret that binary data that's being stored. That brings us up to potential future stuff. We have about 10 minutes for this, so I won't spend too long on any one of them. Obviously, all the things I've just talked about, they're going to continue to be iterated on. They're going to get sort of gradually better and better. That's great, and it's great for our usability and our day-to-day lives, but it's not like cool or sexy, and I want to talk about stuff that is cool and sexy. So, DNA data storage. DNA is very, very data dense. Microscopically small cells can hold the entire genetic code for an entire animal. And there is a team at Los Alamos National Laboratory who have created an encoding for turning binary data into DNA-friendly pairs of A, C, T, and G bases. The idea is you can create synthetic DNA, and then that DNA at low temperatures is very, very physically durable, could be stored for a very, very long time. There is DNA data on the moon, courtesy of the Bereshit lander in April 2019. It did crash, so we don't know if the DNA data is still good. I actually don't know what was stored in it, but I know that it was stored in synthetic DNA. If it isn't lost, then the Arch Mission Foundation, who ran this mission, they built and sent the lander. They estimate that it could still be legible in billions of years if people know how to interpret the encoding that's in it, and they have the physical machinery to read the data out of this synthetic DNA, which I think is really, really cool. So physically, very, very durable. but the encoding is the fragile part. And that is the thing that we're finding is the real problem as we try and design things for the future. We have the technology to make physical hardware that's incredibly durable, but whether or not we can actually extract meaning out of that physical object in the future that's an unsolved problem. And it's something I'm actually going to talk a little bit about in my second talk today at 3:00, so come and see that. It's all about communication. And that's also a problem that we see when we talk about the next thing I want to talk about. This is called Superman storage, named after the Kryptonian memory crystals in Superman. It's also called 5D optical data storage, which is equally as much a marketing term. It doesn't have 5 dimensions, really. It's got 3 dimensions and 2 degrees of freedom. But what it is, you take a bit of transparent, non-photosensitive material, like a chunk of fused quartz or toughened glass, and you use a laser to engrave data within it at a very small level. It's called 5D because you've got obviously your 3 dimension of depth, width, height, and then the other 2 degrees of freedom that they're counting as dimensions is the angle that you're looking at the object from and how close you are to it. So 5 degrees of freedom, essentially. And depending on how close you are to it, where in the glass you are looking, and so on, you can read this laser engraved data out. And this photo is of the Universal Declaration of Human Rights engraved into a piece of glass, and it's very cute because they've made it look like the UN logo. Cool. Hitachi and Microsoft have both been working on this concept. The current bleeding edge is, I believe, being developed at the University of Southampton in the UK. Again, yay, UK. All of these teams are working on this idea with the explicit goal of data durability. This data isn't going anywhere. There's no MOSFETs to leak. If you put a magnet near it, it's totally fine. You can drop the glass, obviously, and then the glass will shatter and the data will be lost. But barring that, this data is physically very, very durable. However, if you find this piece of glass, how can you know what the data engraved in it is? I mean, the data is also visual. You don't necessarily need a computer to get 1s and 0s out of it, but you do need to know what those 1s and 0s mean. And that's the problem that's being worked on at the moment. I don't know what encoding was used to make this particular piece of data storage. It might be in there in 7-bit ASCII for all I know. But if we know how to decode that in 1,000 years, we'll be able to get the UN Declaration of Human Rights back out of this piece of glass, which is really, really cool. Right, the last thing, weirdest thing. Get really weird with it. This isn't a time crystal. Do we have any condensed matter physicists in the room? I have given this talk and I had someone put their hand up and I was like, I'm so sorry for what I'm about to do to your beautiful discipline. This up here, this is not a time crystal. There are no good photos of them, unfortunately. This is a space crystal. And like flash memory, you have some in your pocket. This is silicon. The thing that makes it a space crystal is that it has a recurring structure in space. You look at one area, then you translate in space, and you look at another area, and it looks very, very much the same. A space crystal, recurring structure. Time crystals are the same thing, but they have a recurring structure in time. I don't think there are any actual photos of a real time crystal, but this GIF is kind of the closest thing I can get to visually explaining what I mean. A time crystal is an object whose lowest energy state, its resting state, is one of motion. This doesn't break the conservation of energy because something quantum physics. They were first theorized to exist in 2012 by a theoretical physicist called Franz Wilczek, and in 2021, only 9 years later, a team of scientists at the University of Hamburg made one in a lab. It didn't look like what we'd think of as a crystal. It was a Bose-Einstein condensate, which is a state of matter you get when you supercool boson gases, as of course we all know. I hate when I open up my freezer and I've made a Bose-Einstein condensate again. But they made this in a lab. And the reason that they're in this talk is because some very clever people think that we might be able to use them as some sort of memory storage for quantum computers. That's currently an open problem, as I understand it. In quantum theory, there's a thing called the cloning theorem. And what the cloning theorem states is that you cannot duplicate quantum state. So if you were going to store quantum state memory for a quantum computer, you can't copy it. You can only place it. And then if you wanted to read back out of that memory storage, it would be destructive readout, just like with core memory back in the 50s. And yeah, people think that time crystals might be something that we can use to store quantum state durably over a long time with sort of a low rate of decoherence. I am far from an expert in this, but I think that's really cool, and it means I get to talk about time crystals as part of this talk. But yeah, it would be destructive readout, just like core memory. What's old is new again. Time crystals. I read the Wikipedia page for these briefly comprehended them, had like an out-of-body experience, and then I lost it, and I don't understand them again. Honestly, even just the Wikipedia page for these things is just like such a wild ride. I really encourage people to go check it out. They're really, really cool. Some very, very clever people doing some incredibly hard maths and physics. Right. That pretty much wraps me up. We've learned about storing data all the way from the Bronze Age, customer complaints about Air Nazir and his copper, all the way through floppy disks, hard drives, and maybe putting DNA data, well, definitely putting DNA data on the moon. We did that. This is an incomplete whistle-stop tour, and the real takeaway that I want to pass on to you here is that humans are so cool and creative, and we're very good at making really complicated hardware. Just like so much cool stuff that all has contributed to what we do today as developers. But the other takeaway, I guess, is the point about data durability. The physical sort of durability of the objects we use to store information is, of course, important. But the thing that's actually becoming more important as we move forward into the future is the ability of people in the future to get information out of the objects we use today to store data. If your encoding is lost, like it very nearly was with the Mars Viking lander, whatever effort you put into storing information is wasted. Storing data is all well and good, but somebody else also needs, maybe you in the future, maybe somebody else needs to be able to read that data for it to be valuable in any way. There's something to bear in mind. It's why we document things, right? And just, as we store data, make sure that we're doing it with the eye to the fact that somebody else is going to have to read it eventually. Thank you very much. That wraps me up. That link, that QR code there is not a Rickroll like the one earlier, but it takes you to a little feedback form where you can just a free text field. If you'd like to give me any feedback, I really appreciate it. Thank you so much for being here. I hope you've enjoyed this talk, and I hope you enjoy the rest of the conference. It's going to be really, really good. Thank you so much.